Um, Good afternoon, everyone. So this is the NPTEL problem solving session for week 2 of the course Robotics, Basics and Selected Advanced Concepts. So we'll keep admitting everyone as they come, and like if nobody attends, then we'll just record this lecture and upload it on the channel where people can watch it afterwards. So the topics that were covered in this week were like the topics related to robotics and mathematics. Uh, I will touch upon mainly three topics. Okay, one is the DH parameters. The other is forward kinematics, and the last topic that I'll be covering or touching in this is inverse kinematics. So as sir has already like told something about much about these concepts, I will just be going into some of the derivations that from where the results that are shown in the lectures, where do they come from. So I will start with the DH parameters. Okay, so DH stands for Devankt Hartenberg parameters. Okay, so these are just the name of the guys who devised these parameters. Like you can check the spelling if you want. So what exactly is DH parameters? It is just a way of, you know, it is just one, one particular way of assigning frames. This is G. Assigning coordinate system, or I should just write frames. Frames to each link. Okay. Here link is a single rigid body of the system. Okay, and why we need to assign frames to each link and what we do with these frames, sir has already discussed in the class. So I will again just briefly discuss, these, the convention that we use to assign frames. Okay, that we'll be using. Okay, so let us say this is an arbitrary, link, right? And this link is connected to two other links through these revolute joints. Okay, so and this is the other revolute joint, right? And this is the other link. Okay, so I'll just show the axis, okay, of these joints with this red line. Okay, and mind it, the shape of these links can be arbitrary as it is shown, and even the relative orientation of these axes can be arbitrary. Okay, but the only requirement is that the links should be rigid, and these axes, they should just not change in between, the relative axis between any two bodies. Okay, so how we start naming all these, assigning frames, is that before assigning frames we need to assign a number to each body, right? So I call this that this is my you body I. Okay, so the ith body, and the next one is, okay, body I or link I, and this is link I plus 1, and this is link I minus 1. Okay, so now comes the actual difference in the different, DH conventions that are out there. So there are multiple DH conventions. The one that we are using is also described in the book by J. Craig. Okay, so that I will just write the name of that book. Okay, okay, so it is called Introduction to Robotics, and it is written by J. Craig. Okay, so we'll be following the convention that is described in this book, and it is also sometimes called the Craig convention. Okay, like, so what this convention is actually, this axis, you know, the axis between, that is connecting link I minus 1 and link I. Okay, this axis is called ZI. Okay, so the ith frame, okay, or the Z axis of the ith frame is the axis of revolution between link I and link I minus 1. It is not just about the revolution, it is just about any kind of displacement. If the displacement is angular displacement, then it is about the Z axis. And if the displacement is linear displacement, then it is along the Z axis. Okay, so the axis ZI or ZI, whatever you want to call it, is between link I minus 1 and link I. Okay, so similarly, this axis, okay, that is between I and I plus 1, it is called ZI plus 1. Okay, so of course, as we said that these, both the axis, they are not just the axis, all the links, they are arbitrarily, arbitrarily shaped, arbitrarily placed, arbitrarily oriented with respect to each other. Okay, so these two axes, as long as they are not intersecting, okay, they can be oriented like any, in any manner they in space. Okay, but there will exist a line connecting the nearest 2 points, you know the line of shortest distance between these two axes. The drawing is kind of a bit bad here, but you get the point. Okay, so this green line is the line, that is denotes the line with the shortest distance between Zi and Zi plus 1. Okay, and this is how we define the next axis of our frame. Okay, so this is what we call, okay, so the line So these points actually, okay, these intersecting points of this green line on the both of the red lines, they become the origin of our coordinate frames. Okay, so this point becomes origin for the ith one. Okay, and for the I plus 1th one, it will be decided by the further next link, that is the I plus 2. So the line connecting Zi and the I plus 2, okay, I like wherever it might be, that will decide where is the origin for this frame I plus 1. Okay, but for this, the xi is along this line right here. Okay, and again, it's like the x I plus 1 can be like anywhere, okay, on this zi plus 1 line. Hmm. So you see, we have the two axes, but we need three axes to define a coordinate frame, right? We know this. So where we will get a third axis is the assumption that we are using, okay, so we are using right-handed coordinate system. Okay, so this is how the third axis or the direction of the third axis gets defined, because now if we are following the right-handed coordinate system, okay, this means that you know whatever x cross y gives z. This is the cross product. Like I should write xi cross y is zi, and similarly going through like the combinations, zi cross xi is yi. Okay, so since I have zi and xi gives me the direction of yi. Okay, so this is how we will get the direction of y, and that completes the coordinate system. Okay, this is yi. Okay, so now the next thing that was discussed in the lecture is how do we express the relationship between these two frames, that is zi plus 1 and zi. Let us say that this is yi plus 1, right? And the yi plus 1 and yi are not parallel. Okay, they can be rotated, arbitrarily oriented in any manner. Okay, so now to connect, get the relation between the two frames means getting the total transformation. Okay, connecting the I plus 1th frame to ith frame. Okay, so you see, now when I say about the transformation, it means there should once I apply this transformation to my ith frame, okay, or once I let us not give indices for now. Okay, I just want a transformation, okay, that when applied to ith frame converts the ith frame to I plus 1th frame, or by like saying it in some other manner, makes the ith frame coincide with I plus 1th frame. Okay, so now like it is pretty clear that to go from ith frame to I plus 1th frame, okay, there are certain, you know, motions that you can do that will make you reach there. Okay, so one of them is the rotation about xi. Okay, why rotation about xi? To align, because this zi and zi plus 1, they're not aligned. Okay, so to align, like let's say if zi plus 1 is like this, then zi is something like this. Okay, there is some angle between them. Okay, and this angle is what you know from the lectures is called alpha. Okay, alpha I. Okay, so like to go from frame I to frame I plus 1, okay, what are the set of transformations that we need to do? Okay, so we identified that first one is rotation about xi axis by alpha I radians. Okay, so once the frame I is rotated about the axis xi, okay, the z axis of both the frames are now aligned. Okay, so the next step is to translate the new, okay, next step is to translate this new frame about xi. Okay, so now the first one was rotation about xi to get the zi or the z axis of both the frames parallel to each other. Now the next step is the rotation about xi. Okay, so after the rotation, not just rotation, the next step is the translation. So translation about xi by bi, not di. Okay, we'll call it ai. Okay, and this can be in, like, again, any units that we want. We'll say that this is in meters. Okay, but let us not keep the units here. Okay, it is just a rotation about some angle alpha, and then it is just translation about some angle, some distance ai. Okay, so now let us see. So now let's see how do the two frames look after these two transformations. Okay, so okay, zi and zi plus 1. Okay, they are now parallel to each other, and now after the translation they coincide. Okay, but the OI, the origin of the ith frame, is here, and the origin of the I plus 1th frame is at a different place on the same axis. Also, the x-axis of the ith frame, okay, like it passes through the origin of the ith frame for obvious reasons, right? And the x-axis of the I plus 1th frame, okay, it passes through a different origin. Okay, and again, if you see, these two lines need not be parallel or even coinciding, okay, to each other. Okay, like they can be oriented arbitrarily in 3D space. So what are the next two transformations that we need to make is, like, just remember that our final goal was to make frame I coincide completely with frame I plus 1, right? That will give us the, you know, motions or the steps that we need to take to transform frame I into frame I plus 1, right? This is what we mean when we say that frame I should coincide with frame I plus 1. Okay, so now clearly the next transformation that we can do is, you know, we can rotate the xi axis about z. Now it doesn't matter if I say zi plus 1 or zi, because now they are both coinciding. Okay, so I rotate about, I give a rotation to frame I about the z axis of the new frame by an angle that I call theta I. Okay, let's call it theta I plus 1. Okay, so what it will do is it will make the x-axis of both the frames parallel. Okay, they still won't coincide, but it will at least make them parallel. Okay, I can call it rotation about z I plus 1, or like, you don't even need to call it z I plus 1. It is just the new axis. Okay, the new z I slash I plus 1, anyone, by theta I plus 1. I call this angle theta I plus 1. Okay, and once these x axes of both the frames coincide, the last thing that remains that separates these two frames is this displacement between the two origins. Okay, and this displacement is called the, like, we'll name all these different transformations, but let us give the name to it right now itself. It is the link offset. Okay, so once I do this, you know, translation about z axis, okay, like, again, it doesn't matter if it is I or p plus 1, by di plus 1. Okay, so after these further two transformations, both of the frames, okay, like, they perfectly coincide with each other. Okay, so zi and zi plus 1 coincide, both the origins coincide. Okay, like, always remember that to say that two frames coincide, all the three axes and the origins should coincide. Okay, a frame or coordinate system is defined by not just the three axes, but also the origin. Okay, so you need, let us say, I call a frame A. Okay, or why call frame A? Okay, we have already defined some frame, right? Okay, so the frame I is defined by the origin and the basis vectors, or what we call axes of the coordinate system. Okay, basis vectors and the origin. Okay, so we needed to make all of them coincide. Okay, to get the transformation. And after these four transformations, this is how all of them look. Okay, and again, we know that since xi and zi coincide for both of the frames, and y depends on z and x only, then y of both the frames will also coincide, right? So now we have, in terms of the motions that we need to do, that what is the transformation? Okay, transformations means a motion, right? You are moving something in some way, like you're either moving it linearly or you're moving it angularly, right? So this first transformation that we did was, this is called this alpha I. Okay, this angle is called twist angle. Okay, this second transformation, okay, so we translated about xi by an amount ai, right? So this amount ai that we had to translate, was it is called link length. Okay, similarly there is name for these two as well. This theta I here is called the joint angle, and this di here is called the, like, whatever you want to call it, joint offset, link offset, or frame offset. Joint. Okay, so these are just the names. Okay, now what you had was, in the later stages of the slides, sir had given you an expression for the net transformation matrix, right? Something like this. Okay, and it was a function of, all of these quantities: alpha ai, theta I plus 1, and di plus 1. Okay, and I think this would be more familiar, in terms of, so this expression was a matrix. Okay, it was a 4 cross 4 matrix. Okay, that had terms that depended on these four quantities, right? ai minus theta I di. Okay, so see, this is just a convention of how you know assign frames to any link, and how you get the transformation between those two frames, because then you can, express quantities that in, let's say, I plus 1th frame in ith frame. Okay, and that is pretty useful at many points. Okay, so how do you get the expression that sir had, that was given in the slides to you, is you look at these four transformations. Okay, so we said that if we do these four transformations, okay, the frame I coincides with frame I plus 1. Okay, it means these four transformations have the information of the relative orientation or the relative transformation between frame I and I plus 1. Basically, they have information about this T. Okay, so how we get this is, so see, it is how they're related is, well, first of all, what we need to see is a very small concept called concatenation of transformations. Okay, so this is also useful in case of rotations. Okay, when you're dealing with either Euler angle or fixed angle rotations. Okay, so what it essentially says is that if I have some initial frame, okay, let us say I have this Fi, and then I apply transformation T1, then I get, let us say this is F1. Okay. After transformation T1, it gets transformed to F2. Okay. Now I apply another transformation, but this time this transformation is with respect to F2. Okay. Like basically I'm transforming with respect to the new axis, basically either rotating about the new set of axes or translating about the new set of axes, right? That we are essentially doing in these cases. Okay. I rotate about xi by an angle alpha I, and now about I take the new frames. Okay, I take the new coordinate frame that I get after this rotation number one, and then I translate that new frame about xi. Okay, to get f3, right? So if I talk about the combined transformation from f1 to f3, okay, so this transformation will be given by the right multiplication of the matrix form of all these transformations, right? You write all these transformations in matrix form, and then you multiply them one by one, okay, to the right. And if there is another transformation, T3, okay, that is again about new F3 axis or the F3 frame, okay, then you will just multiply it to the right again, okay. But what is this? Okay, if the transformations, okay, like let us take again the case of frame F1. Okay, I do a transformation T1. Okay, and the new frame is F2. Okay, after transformation, after some transformation. Okay, I either rotate the frame F1 or I translate, move the frame F1 in some way. I get a new frame, and then I further transform this frame F2. But now this transformation, okay, it is about the previous frame itself. Okay, it is not about the new frame. Okay, so let's say I rotate. I'm talking about frame F1. I rotate, let's say by an angle alpha I about the x-axis of F1. Okay, and then I rotate about the y-axis of the same frame F1. Okay, so now this, if I say that these are just rotations, then this second rotation is not about the new axis, that I get after T1. Okay, these are about the same axis as F1. Okay, so in this case, when we talk about the concatenation or the final transformation, okay, so in matrix form, it is given as the left multiplication, okay, of all these transformations. Okay, so if you keep transforming with respect to the original frame, you left multiply. If we keep transforming with respect to the new frame that you get every time, you right multiply. Okay, now with this knowledge, going back to what we actually know that we did while transforming frame I into frame I plus 1, is that each and every transformation that we have written here is about the newest axis till that time, right? It means that if I call the transformation 1 as, a rotation about x-axis by angle alpha I, right? And let us just write this also, that there is no translation as of now. Okay, now the second is no rotation. It means an identity matrix. Okay, but now there is a translation about x-axis distance AI. Okay, third one, transformation. Third transformation is rotation about the latest z-axis by angle theta I plus 1. Okay, and then again no displacement. And the final transformation is no rotation but a translation about the new z-axis by angle by distance di plus 1. Okay, so let me call this T1 and this T2, this as T3 and this as T4. Okay, so according to the concatenation rules that we have learnt above or discussed above, that the matrix from, okay, when you write the matrix of the transformation from frame I plus 1 to I, all these successive transformations will be right multiplied. Okay, so this T1, T2, T3 and T4. Okay, and now once you write their matrix form and actually do multiply them, okay, then you will get the same, result as this as Saresh had shown in the lectures. One more thing, if you see, or both these transformation 1, 2 and 3, 4, okay, they are the rotation and displacement about the same axis. Okay, so we can actually combine 1 and 2 to, let's say, form a TS1. Okay, this is what you have learned as a screw displacement in lectures. Okay, when there is a rotation and displacement about the same axis. Okay, that is called a screw displacement. So these four different transformations, you can replace them by two screw displacements. Okay, where TS1 is, a transformation where there is a rotation about x-axis by angle alpha I, and there is a transformation about the same x-axis and a distance AI. And just keep in mind, I'm using indices I plus 1 and I. Okay? In lectures, it is I and I minus 1. So you just need to change them accordingly. Okay, so this is your first screw transformation. And the second one, if we see, these are rotation and translation along the same z-axis. Okay, so it is a transformation where there is a rotation about z-axis by an angle theta I plus 1, and there is a translation about the same z-axis by a distance d I plus 1, right? So rather than writing these four different matrices, that will then eventually combine to give you the same result. You can directly write, the complete matrices once you have this intuition about screw displacement, that what the actual what kind of motion is happening here. It is actually screw displacement. Okay, so once you have, these transformation between, you know, different links, you can write it in either form, right? Like this is just notation. Okay, so what you can actually do is you can define a base frame, okay, and then you can define frames for every link on your bot, okay, and then let us say you keep defining frames and then there are many frames on your robot, okay, and then finally you assign a frame n, okay, frame called fn here, to the tool of the robot, okay. Now how do you get the, now it will be something, you know it can be any complicated arrangement of, different kind of joints, different kind of links, they will all be rigid but the shapes can be arbitrary, okay. So there is a tool at the end, okay, and we want to know the position of the tool with respect to, let's say, a base frame that we have defined, this f naught frame, right? So if we say that we have assigned a frame fn here, then if I express, you know somehow I can express the origin of this frame in f naught frame, okay, that will directly give me the position of, position of this tool or the end effector in base frame, okay. Now clearly we can see that the origin of nth frame, as seen in nth frame, okay, this is, you know as seen from nth frame, if I write the coordinates of the origin, they are clearly, you know it is a zero vector, okay, and I will mention here also this is in nth frame, okay, and what we want is origin of the nth frame in zeroth frame, okay, and we know how we do that is, we use the transformation from the nth frame to zeroth frame, and that transformation actually allows us to get something like this, right? So we have to change all the coordinates from the R3 space to a homogeneous R4 space, okay, to use homogeneous coordinate matrices, that is basically to use these T matrices, okay. So we know this, O, N, and 1, okay, like this quantity, just this quantity here is just, you know 0001, okay. What you actually need to know to calculate, you know how does the origin of nth frame look in zeroth frame is this matrix Tn, Tn0, okay. But rather than calculating it directly, now you have a method to calculate it, okay. How do you calculate it is you can decompose it into, consecutive frames, relation between the consecutive frames that you have assigned to the consecutive links, or you can say assigned at the consecutive joints to the links, right? And then this goes on till n minus 1 and n, right? So once you have the DS table, you can write these individual P matrices. Using these P matrices, you multiply all of them. Okay, when you multiply them, you will get Tn0. Once you have Tn0, okay, you multiply it by this 4 cross 1 vector. Okay, this is a 4 cross 1 vector, right? 0, 0, 0, 1. Okay, so if you like think about it a bit, okay, let us say, uh, let us assume a structure, not assume, let us see what will be the structure of Tn0. Okay, there will be a rotation part, you know, from frame n to frame 0. Okay, like this will be a 3 cross 3 matrix. Okay, then there will be a translation vector again, some translation part. This will be a 3 cross 1 vector. There will be a 1. Okay, and then there will be just a 0 row vector. Okay, now if we multiply this matrix by 0, 0, 0, 1, okay, what you essentially end up getting is, let me just mark that Tn plus 1 is only, this quantity. Yeah, what you will actually get when you multiply is directly the last column of the matrix. 1 and 1. Okay, so now you know that how will the origin of nth frame look in zeroth frame or the base frame. It will just be the translation part of the T0n matrix, right? Okay, so now I think, so once you know that, you know the translation, the this displacement of the origin of frame n from origin of frame 0. Okay, you can express, the coordinates. You can write the coordinates of your end effector in your base frame. Okay, let us take an example. Okay, we'll take an example of a simple 2R robot. Okay, so first we take a look, you know, first we will assign some coordinate frames, right? So you see, this is link 0. We can say the ground link is link 0, right? And then this is link 1. This is link 2, right? So what we do is we assign the 0th frame right here. Okay, this is x0, y0, and z0 is coming out of the plane, right? Now z0 and z1 will coincide, right? Because you know the this link 1, is here, and the joint between link 0 and link 1 is called the joint 1, right? So the z0 and z1 will coincide. Okay, and the joint axis here, similarly, out of the plane, will be called z2. Okay, so resultantly, consequently, this, you know this is how we'll be defining xi. Okay, along the line going from z1 to z2. Okay, so this is your x1. Okay, and again, as we talked, we can know where is y1. Okay, now to get y2 or x2, you need a z3, right? So to get z3, what we do is we assign a frame. Okay, that we say that will be parallel to the second frame. Okay, so we only know about the z-axis, so we say that there is a z3 axis on the end effector. Okay, so seeing this, the x2 will be along the second link, right? Connecting z2 and z3. And then we can know y2. Okay, and since we said that both the frames, z frame 2 and frame 3 will be parallel. Okay, we get x3 and y3. Okay, so if you try to make a DH table for this particular system, for this 2-hour manipulator, okay, okay, so we have alpha I minus 1, ai minus 1, d theta I, and di. Okay, and then we have links 1 and links 2. Okay, so we see that alpha I minus 1, that is alpha 0. Alpha 0 means the twist between z0 and z1. Okay, the twist here right now is 0, right? And then there is a I minus 1, that is a0. Oh, and there is this third frame also. Just I need to, since we have assigned the frame, we need to include it in the DS table. Okay, like a0. A0 is the displacement or the distance between z0 and z1. Right? This is also 0 here. Then we have theta 1. Okay, theta 1 we know is the angular displacement, or the between x0 and x1. Okay, so this is, so we define here, this is here as theta 1, and this angle here as theta 2. Okay, this angle theta 1 from base to the link, and from first link to the second link we define theta 2. Okay, so now this becomes theta 1. And like, what is d1? D1 is the offset between x0 and x1 along z, right? So this is 0 in this case. Okay, so similarly, if you keep writing these values for all these frames, you will end up with this DH table. Okay, once you have DH table, you can easily calculate your T01, T21, and T32, right, using this table. Okay, and once you have those, you can calculate your like, you will get the matrix form of all these, right? There should be no doubt. Okay, we are only dealing with matrices here. Okay, you will get this by multiplying all of them, right? Combining the transformations. Okay, so what you will get is something like this. Okay, I have abbreviated some things here. I will explain what they are in some time, like once I finish writing. 0, 0, 0, 1, the common things, and then there is L1 C1 plus L2 C. Let us call it 1 2. Okay, so 1 2 is, no, I'll keep it 1 plus 2, and then L1 S1 plus L2 S1 plus 2 0. Okay, you will get this after you multiply all these three matrices, right? So we know that the frame 3 is our end effector frame, right? And what if I want the coordinates of my end effector as seen in base frame, right? This is what we were discussing here, right? How do I get the coordinates of my end effector, that is this guy right here, as seen from my base frame? Okay, like this is where the I is, right? So what we had concluded was that the translation part of the final transformation matrix between the tool and the base frame gives me the coordinates of the end effector plus L2 C 1 plus 2 L1 S1 plus L2 S1 plus 2 0. Oh, and about the abbreviation, C theta is just cos theta, S theta is just sine theta, and let's say C alpha plus beta is just cos alpha plus beta. Okay, so this is cos theta 1 plus theta 2, right? C1 plus 2 is cos theta 1 plus theta. So these are just like shorthand notations that I have used for writing the trigonometric terms. Okay, so like this is the whole point of why we actually do assign DH parameters. Okay, what we actually need to do, we just want the transformations. Okay, the final transformation matrices. Okay, between any two frames. Okay, so now from here we will progress towards the next topic that we had to discuss, that we will discuss, is forward kinematics. So the whole point of forward kinematics is that you know there is a robot, okay, and there is a base frame to which the robot is attached, okay, and then there is an end effector, okay, or the tool, okay, and you are interested in manipulating this tool, okay, and let's say this tool, you know the position of this tool is given by x and y in this Cartesian plane, right? This is your x0 and y0, okay, but generally in robots you cannot directly control these coordinates of the you know end effector. Okay, but what you can control is the relative angles, right? Okay, or the joint angles between any two links, right? How does it happen? Because all the different links, they are connected through motors. Okay, so you know there is an input, that is theta 1 and theta 2 in this case, and then there is output, that is x and y in this case. Okay, so the function that maps input to the desired output, okay, that map is called the forward kinematics. Okay, so if I say that the vector x is the vector of this coordinate x and coordinate y, and the vector theta is, yeah, just writing everything in matrix form, then this x equal to, it is a function of theta, right? The x, these end effector coordinates, they depend on your joint angles. Okay, so this mapping from your joint angles or from your controlled quantities, okay, because we are saying this is input, it means user gives this input, okay, or even if not users, these quantities can be controlled either by the user or by some intelligent algorithm. Okay, controlled, or as they're also called, actuated quantities. Okay, and these are what we desire to control. Okay, so this mapping F is called the forward kinematics. As simple as that. And how do we get this, the coordinates of the end effector? Okay, we have seen, you know, this procedure in the previous section that we discussed, that we just, you know, take the translation part of the final transformation matrix between the end effector frame and the base frame. Okay, so like we'll continue the example that we were taking of the 2R manipulator. And okay, so this angle here is theta 1. This angle, relative between link 1 and link 2 is theta 2. This is the end effector, and let's say the end effector coordinates are x and y, right? We are not writing z because this is right now a planar mechanism. So anyways, z is equal to 0, and that we could also see in the expression that we got finally, okay, for the coordinates of the end effector. Okay, so the x here is L1 C1 plus L2 C12, L1 S1 plus L2 S12, and 0. Okay, so these are like respectively the x, y, and z coordinates as seen in frame 0. Okay, or we can write F0. We should just know that what frame these coordinates are written in. Okay, so these, you see, this is a function. I can say this is a function of theta 1 and theta 2, right? This, there is a theta 1, theta 2, because all the other quantities are constant. L1 and L2, they're constants. Okay, so this is actually the forward kinematics mapping or the forward kinematics function for the 2R manipulator. Okay, that is x equal to L1 C1 plus L2 C12, y equal to L1 S1 plus L2 S12. Okay, so using this mapping, given any set of values, given theta 1, theta 2, we can calculate x and y. Okay, so this is actually what forward kinematics for serial manipulators with fixed base is. Okay, but what happens is, more practical problem is that when we are given some value, okay, so a more practical problem is, given x and y, what is, the corresponding theta 1 and theta 2. Okay, this just means that we know where the end effector should be. Okay, we know where we want the end effector to be. Okay, let us say we want it to be here. Okay, we know the coordinates x and y. Now, what are the joint angles, okay, that are required to reach this position? Okay, so now you have some desired output, and from that you want to calculate the input. Okay, so this mapping from the desired output to the input, okay, where the input is the same as we discussed in the forward kinematics, that is the actuated quantities. Okay, this mapping is called the inverse kinematics, IK. Okay, the above one, it is called the forward kinematics, FK. Okay, so going from, now with respect to forward kinematics, it is an inverse problem, right? Because forward kinematics is this. Okay, and we are saying that inverse kinematics, we can also write this as Fk of theta, right? This is Ik of theta, or you can also write G. It is just what you want to call a function, it's up to us. Okay, this is the inverse. Oh, no, not theta here. Okay, given the x vector, it is just the inverse function of forward kinematics. Okay, theta equal F inverse x. Now, again, we will calculate it for a 2R manipulator. Okay, now we won't be drawing, like, we can make the diagram again. We actually have everything that we need to formulate the problem and then solve it. Okay, so what we have is, we have a relation between theta 1, theta 2, x and y, right? And again, these are connected by L1 and L2. They are the lengths of these links. Let us, write this in complete form. So x is L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and similarly y is L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Okay, now what we want is, we want theta 1 as some function of x comma y. Okay, right now it is, you know, x as some function of theta 1 and theta 2, right? And y as some function of theta 1 and theta 2. And now we just, want to get the inverse functions. Okay, so the first step is we square and add x and y. Okay, so why we are doing this is we are trying to eliminate one of these angles, okay, from these equations. Like you might have seen this in the lectures also. Okay, so when we square and add the first two terms here, okay, only L1 square will remain. Okay, same for the second two terms. Okay, only L2 square will remain. Okay, because cos square theta plus sin square theta is 1, right? And then the last term will be cos theta 1 plus theta 2 cos theta 1 plus sin theta 1 plus theta 2 sin theta 1. Okay, so this actually becomes to L1 L2. Okay, this is an identity of cos A minus B, right? Cos A cos B plus sin A sin B. Okay, this becomes theta 1 plus theta 2 minus theta 1. So the theta 1 gets cancelled out here, right? So we were doing this because we could see some kind of structure that will make this happen, right? Now we have eliminated theta 1 from the whole equation, and what we are left with is this equation, 2L1 L2 cos theta 2. Okay, now I if we rearrange this equation, okay, we will get something like this y square minus L1 square minus L2 square by 2 L1 L2. Okay, so this is the cosine of theta 2 that we have calculated. Okay, now we might be tempted to, like as sir has also explained in the lectures, that we cannot just invert this right here to get theta 2, right? Because we want the solution between the complete 0 to 2 pi, right? Or from, let's say, minus pi to pi. Okay, so for that, what we do is we calculate sine theta 2 by using this relation. Okay, the standard trigonometric relation that we know. Okay, so the plus minus here denote the two different configurations. Okay, the two different possible values of theta 2 for the same x and y. Okay, so what does that mean? We will discuss in like just a moment. But once we choose a specific, sine theta, either the plus or minus one, then we can calculate S2 as, you know, tan inverse of the value sine theta 2 divided by cos theta 2. Okay, and programmatically, what we want to use is we want to use the function a tan 2. Okay, so what this function does is this prevents this, preserves the quadrant in which quadrant for the angle. Okay, so this sign can be plus or minus anything. So this, we have essentially calculated the theta 2. Okay, now let us, before calculating theta 1, let us discuss what it means to have these two different values of plus and minus here. Okay, so for the, let us discuss here itself. Okay, for the 2R manipulator, let's say if we want the end effector to be at this particular position. Okay, so there are two possible solutions or two possible configurations of the robot in which it can reach, you know, this particular coordinate. Okay, first one is when the robot is like this. Okay, here. And the second one is when the robot is on the other side of this dotted line that we have made. Okay, so this configuration is called the elbow up configuration. Okay, and this configuration is called the elbow down configuration. Okay, so what it essentially means is that plus or minus they correspond to either the elbow up or the elbow down configuration. Okay, so yeah, so this is what the plus and minus in sine theta 2 actually mean. Okay, this is what the two different solutions mean. There are literally, you know, two different solutions for theta 2. Okay, and when seen with respect to theta 1, they just differ in sign. Okay, and that difference in sign is what we have here. Okay, so if we take this to be plus, then it will correspond to the elbow down configuration. This is plus. And if we take it to be minus, then it will correspond to the elbow up configuration. Okay, like simple. Now, once we calculate theta 2, we can, use its value further to calculate theta 1, right? Because now we can assume that we only have one variable, in our system, in our, system of equations. That is theta 1. Theta 1 plus theta 2, and L1 sine, this is y, theta 1 plus L2 sine theta 1 plus theta 2. Okay, so what we will do is we will try to rearrange the terms, okay, such that we decouple theta 1 and theta 2 terms. Okay, right now they're coupled here. Okay, but what we can do is we can open up this cos theta 1 plus theta 2 to get cos theta 1 cos theta 2 minus L2 sin theta 1 sin theta 2. Okay, so we can write this as L1 plus L2 cos theta 2 cos theta 1 minus L2 sin theta 2 sin theta 1. Okay, I just rearranged the terms to write it in this form. Okay, similarly, if I write for y, Okay, if I expand this sine theta 1 plus theta 2, it will turn out to be like this. L2 sine theta 1 cos theta 2 plus cos theta 1 sine theta 2. Okay, now similarly rearranging, just getting, getting all the values of sine theta 1 in one place and cos theta 1 in one place, I will be left with these equations. Okay, so this is now sine theta 1 plus L2 sine theta 2 cos theta 1. Now, if you compare, you know, both of these equations, okay, they look like, I mean, not just look like, they have the same coefficients for sine theta 1 and cos theta 1. Okay, but just, different, like here the coefficient, the first coefficient is for cos theta 1, the same coefficient in y is for sine theta 1. Okay, so if we just make a small substitution that says that L1 plus L2 cos theta 2 is something, r cos phi. Okay, we are just assuming that this is r cos phi. Okay, and this L2 sine theta 2, we can say that this is r sine phi, right? You can say that this is, we assume this particular quantity to be k1 and this to be k2, and since k1 and k2 are two different, you know, variables or two different values, independent values, then we can express them using, the 2D polar coordinates because they are, in 2D coordinate system. Okay, so what we have here is actually, you know, r squared is just k1 squared plus k2 squared. Okay, because we need to know what is phi and r, right, to make this transformation. Okay, to make the substitution actually. Okay, we have this. I call this quantity k1. The second one I call k2. I replace k1. I substitute k1 as r cos phi and k2 as r sin phi. Okay, and then so r comes out to be square root of k1 squared plus k2 squared, and phi is just tan inverse of k2 over k1. Okay, that programmatically should be done using the a tan 2 function. Okay, so this is what the value of r and phi is, and this is the substitution that I'm trying to make. Okay, and I arrived at this substitution, by seeing that there might be a possibility of making an identity of, you know, sine theta 1 plus theta 2 or cos theta 1 plus theta 2, something like that. So x then becomes, your k1 cos theta 1, right? K1 cos theta 1 minus k2 sine theta 1. So this is k1 cos theta 1 minus k2 sine theta 1. Okay, so this then becomes, if I take r common, this is your cos a plus b, right? Cos a cos b minus sin a sin b is cos a plus b. And similarly for y, it will be k1, that is r cos phi, sine theta 1 plus k2, that is r sine phi, cos theta 1. In this case, if we take r common, it becomes sine of phi plus theta 1 or theta 1 plus phi, whatever you want to call it. Okay, now you can see that sine of phi plus theta 1 is y over r, and cos of phi plus theta 1 is x over r. So phi plus theta 1, I can calculate it as this, tan inverse of y over r over x over r. Okay, and of course I'll be using the 8 and 2 function whenever I want to write tan inverse, because that, again, that is what we want to do programmatically, because that preserves the quadrant. Okay, it gives the solution in the full range. So now this leads to 8 and 2 y over r comma x over r minus phi. Okay, and we know what was phi, right? Theta 1 is 8 and 2 y over r x over r minus 8 and 2 k2 k1. So you see, now this k2 k1 and r, we already have the expressions for all of them right here, so we can even substitute them if we want, but we won't be doing that right now. Okay, what we want to see is, like, you know I will just write this in terms of the expression, not cos theta. you know so what we do is we first calculate cos theta 2, using the expression that we had above. Okay, that is, we calculate this cos theta 2, then we calculate sin theta 2, we choose a particular sign for sin theta 2, use based on the particular configuration that we want. Negative meant that we are using the elbow up configuration. Positive sin theta 2 meant that we are using the elbow down configuration. Using the sin theta 2 and cos theta 2, we calculated the value of theta 2, and then further using the value of theta 2 and L1, L2, X and Y, we calculate theta 1, right? And that is this equation. Okay, so from this we get this. So you see, this is the the inverse kinematics solution for the 2R manipulator, right, that we have discussed right here. So I think this will be relevant to whatever assignments you have this week. Okay, because they are all related to DH parameters, forward kinematics, inverse kinematics, right, and also the elimination to get the inverse kinematics, the solution to the forward kinematics equation. Okay, so again, if you have any doubts, you can post in the forums, and next week also, if you have any doubts, then you can join the session and we can discuss whatever doubts you have. So I'll end this session here.